Hi everyone, and welcome to Latte Love live streams. My name is Zach.
I'm John.
And today we're going to really dive in today.
This is going to be a wild one.
Yeah. So today we're going to be going over a little bit of water chemistry and picking out filters. This is largely important in home espresso, commercial espresso, anything that we do. And in order to really teach what we do here when helping you pick filters, we do kind of have to touch a little bit of chemistry, unfortunately.
Yeah, and I mean, I'll admit that water is it's been one of my blind spots for a long time in coffee, so I've been excited about this one. Zach has taught me a lot over the past few days, and we've got some awesome presentations to give you. We're going to show you how to make your own custom water. We're going to show you what a bunch of the filters that we have through BWT can do. It's not only going to help you protect the longevity of your equipment, but also make your coffee taste better.
So make sure that you're putting any questions you have right down below in the comments, because I can kind of get away with myself. You know, I start going too deep into the science side of things, and John is actually here as my translator today. So
that's right.
We'll see how much we can hold on to things today.
I'll be translating for Zach today, and we're both gonna learn a few things, you and I. Here we go.
We're gonna start with molecules. It's funny because that sounds like a joke, but we're really starting
actually
at molecules.
starting with molecules.
All right, specifically what we're looking at is water. So, John, what is water?
Water is a molecule. Did I get that right?
A molecule.
Yeah,
cool.
Pretty cool, man.
Pretty cool.
Yeah,
so water is a molecule. And water is also fighting as hard as it can to stay neutral. And that includes inside your boiler as well. So when we look at the composition of these water molecules, and specifically what's happening within our boiler or anywhere, these water molecules are kind of surrounding other minerals and dissolving it. So surrounding other molecules or other ions and doing so, that's technically what we do when we dissolve stuff. So if we want to picture this in a way, as we dissolve it, it's surrounding things with water molecules. Some things can't be soluble. So that means they can't be surrounded by these water molecules. And we'll actually come to learn these as different things within our water, as permanent hardness. There's a couple other things that we need to look into, like our total hardness, our general hardness. All of these different things are something that we need to test, either using BWT of these test kits that we have, or we're actually looking up local water results to see what's going on with your water. Now, there's a lot of different special cases, too, of finding all these different things within our water as well that we need to look into when filtering our water, which is how we're actually going to pick what we do with these certain filters, whether or not we're using a aqualizer pitcher on this far side over here, or if we're actually having to introduce an RO system and remineralize our water because it's a little too empty. And like I said, water's always fighting to stay neutral, so we'll actually start fighting with that boiler. In a sense.
yeah, and the way that I understand it, Zach, is if your water is so empty, let's say distilled water or RO water, reverse osmosis, that water wants to ion exchange with anything and everything, and it will do it, including the boiler. So it'll find any imperfections, any even like welding spots, things like that, and grab onto. And grab onto the boiler, and that's how you get corrosion in your boiler if your water is too empty, right?
Yeah, it starts transferring electrons basically because of that. So as things dissolve, there's also a sense of things solidifying as well, right? So this has a lot to do with the area that you live in. So when you live in an area with really hard water, what does that really mean? Well, that means that there is a whole bunch of critters inside your groundwater, right? At some point, a lot of calcium, a lot of these salts, these minerals within your water, within the ground, that then dissolve due to rain or runoff or what has you. So the thing about rainwater is that it actually produces carbonic acid to melt these things as soon as it hits CO2. So our atmosphere. Right?
Sure. Yeah.
So as soon as water hits our atmosphere, it has the chance of melting all of these little critters inside your ground, inside the ground, and then end up inside the water itself, which is why it's really important to pay attention to, do you live in a place where it snows, for one, or get a lot of rain? Are you known to have really hard water? These are important questions when you come to us with these sorts of questions. That's how we're going to really choose what filter is right for you.
Yeah, and we did actually look up a bunch of cities. It's all public information. You can actually see what a lot of the water is, the composition of the water in your town or municipality has in it. So we're based in Rochester, New York here. Yesterday we actually took a look at what's in our Rochester, New York water here. So we were able to find all the things that we need to know, really, like our general hardness, our alkalinity, and we're able to do some calculations and even figure out things like our permanent hardness. And that helps us kind of figure out which filters are going to work for us in the Rochester area. So we've also found some hard water as well in our searches as well. For example, like Omaha, Nebraska. And we'll pull up these charts in a minute. We'll show you the differences. But that's going to be the kind of thing where you might want to look into some reverse osmosis and then use a best min BWT filter to remineralize the water.
Yeah, so we'll bring it all the way back down to 0 and then remineralize at that point.
Right.
But it's important to then remineralize with something. And then there's also something like alkalinity that also buffers this change of what's known as pH. So many of us have heard of pH. You use that within pools. I think you test those sorts of pH tests in school for some reason. I don't even remember that class, but I remember doing it. So pH is a great sign of what's going on, but it's not technically what we use, specifically because pH can actually change depending on how much buffering you have. Buffering being the key word here.
What's buffering?
So buffering can actually include basically our alkalinity. So these specific bicarbonates that will basically shield our pH from moving up and down. Now, why is it important to actually keep our pH very similar, very neutral? Is because as soon as our pH reaches a point of 8.2 pH, we can actually start forming scale. And as we know, when we're heating up and cooling down, our pH can actually change quite a bit. And if our pH can move up and down the scale and it can move past that, then when our water cools down, what happens to all these minerals that first dissolved? Well, now they're back to a solid.
And guess what that solid is?
That is scale.
Scale.
So that is lime scale. So that's why it's important to have alkalinity as well, to a certain point.
And so what you're saying is the alkalinity is going to stop the pH from moving around so much and get away from that danger zone, right?
Exactly. So it's important to have that buffering. Now, too much buffering can also be bad. So water is trying to stay right around 7, so things can go acidic and things can go alkaline. And there's a whole other process that's actually happening, whether or not that's going to dissolve, because as we're dissolving acids, that's going to produce hydronium, that's technically what it's called, which will actually increase your acidity. Now, as we dissolve alkalis, which is a whole other thing, we actually increase our hydroxide, which actually decreases our acidity. This is a huge factor when it comes to taste. So that's why when we're adding all these buffers and different things, as we can actually change our acidity, that's why it affects taste so much, specifically.
So we don't want to get to the point where we're getting scale, so we have to control our pH because of that. Mm-hmm. But we also don't want to go in the other direction and have our coffee taste really sour, so we need to control it in the other direction. And that's why we need that buffering to protect that pH. Am I right?
Yep, exactly.
All
so
right, nice.
Let's hop back on over to our total hardness. So we've talked about a couple things so far, and I know it's quite a lot out there, but total hardness is largely important when we're looking at numbers. So if you go look up your water right now from your city, or if you've actually had something like a BWT test drop or titration kit, what that is actually looking for is that general hardness. You might see it as GH, especially on these actual test droplets. You'll also see a bunch of different kinds of units when testing for these sorts of things. So each one of these drops being one general hardness or one degree of hardness. Sorry, 1 degree of hardness, which can actually convert then into ppm. So you'll find that within these, or you actually multiply that number by whatever many drops you get by 17.85. We'll actually give you a graph a little bit later on that you can actually screenshot so you can actually do these calculations at home. But this is what we're actually doing at Whole Latte Love when we're helping you search for your filter. So there's a lot going on here. So why total hardness is important? Well, this is basically broken down into 2 categories, right? So there's temporary hardness. So these things that can boil off and basically melt. Kind of like when we're making a simple syrup. A simple syrup is a great example of a temporary hardness. You can actually see it melt. It's a solvent, you know, and that solvent can also break down and then become a solid again after we warm up and we exceed a certain pH. But there's also things called permanent hardnesses, which is really important when we're choosing a filter because sure, there's these calciums and magnesiums and everything that we can really control, and we actually want these things to a certain point because we can perceive flavor that way. But permanent hardness affects flavor, and we can't actually get rid of it by boiling.
Wow.
Which sucks.
Now, so general hardness, total hardness, that kind of thing, that's more calcium and magnesium, right? Whereas things like permanent hardness might be even things like algae that might not be able to get out with much of a filter, right?
Correct.
Okay,
Yeah, so the other key factor that we look into is actually alkalinity. So the other test drop that we actually have within the BWT tests here. So as you can see, there's that total hardness, so that general hardness right there. Then we also have our carbonate hardness. There you go.
Same thing as alkalinity. You know what I found with these water talks that we've been having and water lessons that we've been giving, a lot of similar names for the same thing. Carbonate hardness and alkalinity, we're pretty much talking about the same thing. And then KH is the abbreviation that would be used for that. So it's easy to get confused there, but we're going to help you along. Don't worry about that.
Yeah, so it is important to actually have a good combination of total hardness and alkalinity. Alkalinity, again, being that shield against our pH really changing, so it's kind of buffering, like we said, and we can add in different things and bicarbonates to actually create that buffer, right? So bicarbonates being a little bit different than our actual hardness. Per se. So these are a lot of things that can also evaporate as CO2 during that boiling process. So it can also change quite a lot.
Mm-hmm. Yeah. You know what, I'm seeing some comments down here. James, hello again. Yeah, chemistry time too. I'd be interested in what Walla Walla, Washington looks like in terms of the water. Apro, in your city, we got 13.4 degrees.
Degrees hardness. So that is actually pretty hard. So we'll actually show those graphs pretty soon here. So we can actually put that 13.4 on the graph when we get there. So
cool. Yeah, sounds good.
So a key thing about alkalinity to touch as well is that you do want it still. You do want these bicarbonates inside here because without this buffering capacity, it's super acidic. Right? That's why on pour-overs too, I feel like we start off with a pretty low number, like a lot of people are shooting for 22s or something on their alkalinity, because then they use little droplets, maybe with bicarbonates and your buffering solution, to then balance out those acids and buffer them down, buffer them out, so it's not as strong. And we start picking and choosing what acids are then going to shine. If you've ever seen little drops like this, and that's why we're really curating water a lot of the time. There's a Goldilocks zone of like what's safe in your espresso machine, and then you get to play around with taste profiles off of that.
Cool.
Which is really fun too.
In fact, we might do that today. We've got 3 espresso machines right behind us, and we're going to put 3 different water makeups in each one and taste some shots and see how it goes.
And we'll go ahead and test that total hardness and alkalinity from those as we go. So,
nice.
So too much buffering can also be a bad thing. If I put too many of these drops, too many of these bicarbonates within my coffee, it's really boring. It just becomes a really bland cup. So this also happens with maybe waters that you see have like maybe a very high pH too. So you need to watch out for that sort of thing. So we're looking for waters that may be towards the acidic side, but keeping in mind that coffee itself is already pretty acidic. It's usually around 5 on that pH scale. So 4.5 to 5. So we're already dealing with something pretty acidic. So if we just had RO water, or the super empty water, not only could it start exchanging these electrons with your boiler, but it can actually start affecting the taste of your coffee as well. Things can be very, very acidic that way.
Yuck.
Yeah. So super gross, right? We don't want that. So what we can go ahead and do now is experiment with this taste. So I have 3 different kinds of machines, or well, I mean, they're all Gaggia Classics. I have 3 different kinds of water behind us, the same grinder dialed in, and we're gonna go ahead and see what a change in total hardness and alkalinity does on our taste.
Cool. This sounds fun to me.
Yeah, let's go ahead and do it. So while you're gonna go ahead and pull this first shot, I'll describe what's happening with this side over here.
Awesome.
So, the side on the red machine that John's about to pull is something that is, I would consider, softened water. So softened meaning a lot of that total hardness has been pulled out. And now what's left are actually a lot of different bicarbonates. What bicarbonates exactly they are, well, who really knows? Unless you have very specific test results. Our BWT test actually can't tell us what's going on with this. So if you want to really dive into what kind of bicarbonates are within your water after softening, I mean, one of the best ways to do that is actually going ahead and testing it. The thing about having 0 total hardness is that it can actually cause a lot of long-term issues, and those electrons still have the chance to start trading out with your boiler instead of attracting to these potassium bicarbonates. So it can still actually create a lot of issues within your machine, although there's still something in there. So just having an alkalinity alone, a high alkalinity and a low total hardness, can be a bad thing, because potassium bicarbonate is actually very volatile.
Oh, wow.
So it'll actually come out, it'll boil off as we're going through. So we can't keep that buffering capacity. Although,
so you're going to lose it all.
Yeah, so although that we're starting like at a very neutral water, it can actually change because coffee itself is very acidic and our potassium bicarbonate is then precipitating. It's leaving a CO2. So how can we trust that? We see a lot of trends actually within coffee right now where people are using a high amount of buffering capacity, which can be a pretty bad thing actually. So with potassium bicarbonate particularly, there's a recipe out there where you use about 60 ppm of potassium bicarbonate and 0 total hardness. This can be a bad thing because it does evaporate, and you still have a likelihood of passing off some electrons, which is pretty bad for your machine. So it's not a full-fledged way to protect your machine. Now, if you're using your machine every so often, it's definitely possible. It's enough buffering capacity so that pH isn't exceeding that level that I mentioned earlier. But let's go ahead and taste it too, because I could assume that there's a lot of buffering capacity approaching our normal levels of like 70, but we'll see how much it can actually buffer out here.
All right, here we go.
So it's definitely on the acidic side, right?
Right. Yeah.
But it's actually pretty smooth. So if you like maybe more acidic coffees, this is something that you can really play with your water. Keeping in mind that you still do kind of want some calcium and magnesium, which is kind of in favor of how BWT specifically makes their water as well. They have their own way of achieving this same sort of taste profile while still having some salts to rely on and create a little bit of a coating and protection to the inside of your boiler. So they do this by actually using magnesium. So they've found that 1-to-3 ratio in favor of magnesium actually helps along with this really nice acidity. It doesn't have too much of this astringency or bitterness. It actually cuts it down.
Oh, nice.
quite a bit, and we can still get a really nice cup while protecting our machine, and we have that safety of that total hardness while our buffering is evaporating out.
And now, the way that I think of salts and things like that in coffee is kind of like what salt does to your food. Salt is, chefs use it to help you actually taste what's going on with the food. The same thing can happen with coffee. Without a certain amount of minerals, it's very difficult to actually perceive what's going on flavor-wise. Now that has to do more with our perception in our brains and on our tongues, and not quite as much to do with the actual extraction happening with that water.
And I think that's kind of the point of like this red machine too. It's like everything's down to 0 and we're just working at buffering, so we can cut a lot of the acids that maybe we don't want, so you can really achieve a nice bright but full-bodied cup. But there's other ways that are a little bit more oriented towards protecting your machine that we can still achieve this, especially if you use your machine often. I would still recommend a BWT. So red machine, it's a pretty good cup.
Yeah,
Lots
not
of
bad.
bicarbonates, potassium bicarbonates, 0 TDS, so very softened water. But let's see what we can achieve with this next one with BWT.
Nice. All right, here we go.
So BWT, they've done a lot of research, actually written a lot of white papers on this specific ratio of this 1-to-3 ratio of magnesium to calcium. So they achieve this by typically a 5-layer step. So they actually have two different kinds of filters. So there's a pre-filter on this first side, then there's a activated carbon filter, then they actually have water running through. You know what's great is that I actually have one right here. Oh, this baby. So what happens here, water actually comes all the way down here, and then it goes through its first layer of pre-filter on the bottom side here. Then it goes through a carbon filter. Then there's actually a whole bunch of ionized beads inside this that will then actually exchange out these different hydrogens. These ion exchanges happen within here that will then create this ratio of calcium to magnesium. So they're exchanging magnesium with calcium through these beads. Then goes through another carbon filter. I believe this is a mesh filter. And then another pre-filter on the top side. Now, there are different bypasses as well that you can use with the Best Flex heads. So those would still go through a pre-filter, but you can actually then go ahead and curate according to taste how much you want with this. And that's one of the coolest things about the Best Flex heads is that you could start dialing in that taste. Now there's lots of recommendations depending on how hard your water is when it comes to something like the Best Max Premium that will actually reintroduce magnesium. Sorry, so this is the Best Min. So this is a remineralization. This is the ion exchange.
Oh, there you go.
Remineralization is a little bit different. There's a little bit of a different step in this. So everything I just said, imagine it was this filter right here that I was describing.
Yeah, this is our ion exchange filter. Now, the
Correct.
Best Min filter you would want to use if you are starting with reverse osmosis and you need to remineralize. You would plug it right into this, and that would add magnesium back into the water so that you don't get pitting and things like that, corrosion in your boiler.
Yeah, so it adds a lot more into your water. So this is all just kind of a safety net. The same sort of safety net that you would do while creating SCA water is kind of happening over here as well. So this is going to be going ahead and introducing some of that total hardness and those bicarbonates back into your water for the best taste and protecting your machine. That's key. But this one ensures that your ratios are staying similar throughout the filtration process. So,
well, I'll tell you what, I got a shot for us. You want to?
Did this just appear in front of you?
Just appeared in front of you.
All right, so we got some Best Max right here, right?
Yep. Yeah,
Nice.
and I'm interested to see what this tastes like compared to that water that's very, very empty, mostly just alkalinity. So.
Yeah, your real comparison is going to be next too, because I created some pretty nasty hard water for the next machine. Okay, this one actually is very much perceiving way sweeter.
Yeah,
so it's
way
interesting
more
what
going on here.
magnesium and calcium can actually do for our perception of sweetness on this. So it's not just utilizing the bicarbonate alone, but right now it's just like an overall sweet cup. I feel like there's a little bit of astringency on that last one.
Yeah, it seemed to help the body out quite a bit too. I'm getting a much more lasting flavor on this one. Oh, and I'm seeing...
Apologize for the slurps too, that might happen.
John Doe, I'm seeing, did he say algae cause permanent hardness?
Ooh.
Not algae, it's turbidity that's algae.
Yeah, so we should probably
good
talk
catch,
about
John.
turbidity. So I did a little experiment. I ran out to our little pond out in the back and fought a goose for some water. And this is what I came out with, right? So it's pretty nasty. It's pretty gross. I recommend not it's a little wet on the outside too. Probably shouldn't touch that much. But what I have here is what you can see is turbidity. You can actually see there's a hue to this. It might be a little hard to see, but it's like that little yellow hue. So what turbidity is actually this collection of what's called colloids. Colloids are actually less than a micron in size and can actually have so much surface area that's like a size of a football. It's insane how much surface area that it has.
Man.
That can also collect diseases. It can collect things like algae. All of these different things can be collected onto this. Now, there's certain ways that we get rid of colloids, which is actually why I have this little experiment right here. So let's imagine that these are colloids. These are these little tiny fine micron things. And I'm adding water to it. And this is currently, my water filtration plant in your local area, right? Mm-hmm. So as I fill this up, it's my... I can see that for a moment there, they were suspended, right? That suspension is the point where it's actually coagulation and colloids within your water. So coagulations is what you're seeing at the top here. So coagulation comes to the top while we actually introduce some things in our water like aluminum sulfites, I believe. Sometimes I get confused between all of these things, that collect to these really small particles so they can actually come to the bottom. Now what we do within water filtration, when we collect them in those large things. I sound so smart and then that happens.
The large, these large...
the large things.
Yeah.
Now this is called flocculation, where it starts collecting at the bottom, and then what we want is towards the middle. So we can turn something like this gross stuff, into that clear stuff right in the center.
You know what's interesting? You mentioned aluminum. When I looked up our local water, a little bit of aluminum does show up in our local water, and they actually compare that against what the acceptable levels are. And the good news is our aluminum level was very, very low compared to what the acceptable level is. So in terms of safety, we're good to go. It's less than like 8 parts per billion is what it was.
Yeah, so don't get confused too when looking at these results, because sometimes they'll throw in like something even smaller than a micron, or like it gets really confused, or they'll change that parts per million and really mess you up a little bit. It'll be a parts per billion.
Yeah,
and then all of a sudden it's like, oh wow, it's really hard. No, it's not. Just so you know.
That particular one was 8 parts per billion, which was like pretty much negligible, but they use a little bit of aluminum to help with the flocculation process to get all these colloids to get heavier and kind of sink to the bottom. Mm-hmm. Once they're at the bottom, just like this, a little tube is put right into just above just below the surface really. We got the oils floating on top and we've got the colloids sinking to the bottom. All the clean stuff is kind of in the middle, and that's the stuff that we want to collect.
Now there's a lot of stuff still within this, which is unfortunate, right? So we talk about, it's like, okay, we're introducing magnesium, calcium, all these things with ion exchange, and we're looking at total hardness. Well, with those permanent hardnesses, a lot of it can still be trapped right here, right? So we still need to pay attention to that. So there's things like pre-filters that we can still use within this, or best taste is a great way to actually protect against some things if your calcium and your magnesium, and all these other numbers are looking perfect. Like let's say you were dead on. Well, there's a lot of stuff that can still make through that we want to look at. Now, if you look at your local water quality results, you can see some of these things. Things like phosphates, the stuff that actually helps soap actually stick to your dishes. So that can actually create like a lot of slime, and it attracts slimes, and it lets things kind of scale in a slime. So algae can also be attracted to those phosphates. So if you live in a farming community, a lot of that soil then ends up inside your, well, not soil, stuff in your soil ends up inside your water, and issues can really happen from that as well. So I have to go to my notes now. I just went off on a huge tangent, but let's see. Let's forget the notes. Let's just keep going. All right, so.
Sounds good to me.
Y'all thought I wasn't using notes, right?
Now, can we all see these down here?
No.
Oh,
so,
that's for us. All right.
That is for us. So while we're actually talking about these total hardnesses, alkalinities, John actually put together a fun little graph that we can do a little experiment right now too, looking at a couple water results, what we're really looking for. So let's go ahead and put that on the screen of comparing water properties really fast. Perfect. All right, so we can see a couple things here. The first thing that I really look for is that total hardness, that general hardness, indicating how much of that stuff is inside my water. Okay, so if we're looking at Rochester, 107. That's not too bad. We're looking at maybe a filter at that point. If we do a quick conversion and divide 107, I have my handy dandy calculator here. 107 0.5 divided by 17.85. We're at about 6 drops. This is actually pretty perfect.
And that's 6 degrees of hardness, right?
6 degrees of hardness. So we're wanting to stay around like 3 to 6 typically.
Okay.
That's kind of like our best taste and area that we really want to be in. So Rochester, we're looking pretty good.
Not too bad.
Let's go down to our alkalinity. So it looks like we have 81 in our buffering, basically. So it looks like it's actually buffered pretty well as well. There's one more thing. In order to get that permanent hardness, you can actually subtract these numbers to get permanent hardness to figure out what else is going on with our water. Are there these other factors that we need to be looking into that might affect taste? So we'll look at that permanent hardness. If there's a huge negative number, well, that can be a very special case and kind of throw off our numbers, and we might need to look at other filtration methods in order to solve that. And a huge key right there also is that TDS. So TDS is another factor that we kind of look into to see just like, okay, quickly, overall, how much stuff is inside there, right?
Right. And, it sounds like the general hardness is going to be things like calcium and magnesium, but that's not the same thing as your overall TDS, because TDS is going to include things like copper, even the aluminum that we were talking about. In fact, Will, can you grab that chart back up there? We're going to look at some of the stuff on the bottom there. Yeah, copper, barium, even the aluminum nitrate. There's a little bit of silica, not much where we're from, but if you look at the only triple landlocked state in the States, Nebraska, much higher numbers for those kinds of things. That's why you're going to see a variance between TDS and total hardness.
All right, so we probably need to discuss what TDS is. So it's basically your total dissolved solids. And when we're actually using something like a TDS meter, what it's actually doing is looking at this current, right? And the ability, it's counting this current between these two anodes, right? And the faster it can actually move and count, the more ions are actually within your water. So that's why it's getting something within that number, but not all of that stuff is actually producing scale. So that's why TDS is something pretty difficult to look at when it comes to acquiring what filter that you really need. It gives us a general idea, but not all of that is going to be providing any sort of scale whatsoever. So the fewer minerals that you have within here, the less it's going to be able to travel, and the less conductivity that you have as well. right?
Interesting. That's how it measures how much stuff is not water. That's kind of how I think of it at least.
Exactly.
Yeah,
How much stuff, ions, things that actually produce a charge can actually go back and forth. That's what it's really counting.
Interesting.
Yep.
Yeah.
So it's the speed of the current between those two electrodes.
And now, you know what might be fun? I'm wondering if some point if you want to do a water test with those BWT titration kits too.
In fact, I have all 3 of these behind us, and maybe we'll even test this as well.
Sure.
And we also even have a TDS meter. But let's go ahead and look at a couple different questions that we have. Whole Latte Love does not condone fighting wildlife. This is true. I didn't really fight the goose. I saw it. He was really mad that I was taking from his pond, but I needed pond water.
I was watching. It did run after him. You made it out alive, though.
Yes. Let's see. So colloids are suspended, non-dissolved particles in liquid. This is true. What's your recs for espresso machines? CaMg salts both precipitate and form scale. This is correct.
Yep.
Just Kana. Biocarbs for buffering should be enough.
Yeah.
This is true. It should be enough, but as we know about biocarbonates, they still are evaporating into CO2. If we are at a place where we can no longer have something stable, like these sorts of ratios of minerals that, we still want something to somewhat protect our machine, and that's what it's kind of being used, but in a very specific amount with this magnesium and calcium. So we still want a little bit for the overall protection of something that is scaling up and down, especially when biocarbonates are evaporating and they're not trustworthy like these salts are. So that's the big thing. So there's I think it's Dr. Palvis has that potassium bicarbonate recipe. Yes, I think that's okay for home machines, but if you're turning on and off your machine a lot of that is a precipitate now. So it's pretty difficult. And think about things like copper or something very conductive that is your boiler. Well, that is actually going to favor that or favor any imperfections inside your boiler than that potassium bicarbonate.
Interesting. So because the potassium bicarbonate, for example, is going to evaporate, eventually you're not going to have that buffer and your pH is going to get all out of whack, which is where you start running into boiler problems, right?
Yeah. I mean, you might want to keep testing your water constantly. And, there's a way that we can actually test this. I mean, go ahead and warm up your machine with that water that we tested over there. Then cool it down, test it again, and it actually should be lower.
Interesting. Yeah.
So,
okay.
Which would be a really fun test that I'll probably do later because we can.
Yeah.
But let's see. We have how much is a factor of water and taste then grind? It's a huge factor. So we can do so much with grind. We can go up and down and stay within ratios and all this different stuff. But if we have a water that gives us the ability to expand on flavor and moving up and down over a grind size and focus on that extraction, then we can better perceive sweetness this way.
Yeah, and to directly answer the question, it's tough for me to rank one over the other. I'm just going to put them both on the same pedestal. Need a great grinder, need consistent grind size, with your choice of fines, depending on if you're using conical, flat, things like that. Need good water too. It's really difficult for me to put one above the other, so I'll just put them both up there.
Yep.
Yeah.
All right, so we've probably talked about different disinfectants too that come in your water as well that start affecting that taste. So if you have something like chlorine or chloramine that's actually used to disinfect your water as is, there's no way that any grind size is going to get away from that bad taste.
Right.
So paying attention to the issues at hand, the first off issues at hand, where you're getting your water from and what is exactly in it, and filtering that out correctly is going to give you guidance of maybe you're just blaming your grinder or your machine on bad tasting shots, or maybe we can actually start blaming the water, which is oftentimes what I end up doing. So I start with water. I start with that darn molecule, and then I go all the way to that darn grind.
So Rob, that might be Zach's answer right there. Zach tends to start with water.
Yep.
So there you go.
Yeah, so I start with water, start at the molecule itself. But if you do need help picking out a filter, well, I do actually have a chart to help us. And as I describe this chart, I actually have a special surprise behind us in this white machine over here.
Oh, yeah.
And if I could describe this white machine, which we will take a little bit of a BWT test of, it is out of this chart.
Out of this world, out of this chart.
Out of this chart.
Nice, Zach.
So, Will, if we can actually go ahead and bring up that water testing.
Nice.
So, created this kind of based off of BWT's filter system. So this is kind of how I occupy my mind of like, okay, where do I need to be, right? I kind of want to follow this line, this nice slope of 1 all the way across this graph here.
So your preference is, if your total hardness is 3, you also want your alkalinity to be 3, right?
I want it to be pretty similar, because remember, if we have a difference here, that is indicating different permanent hardnesses. Or if you look at those special situations there could also be things like gypsum within your water. So gypsum is indicated if a total hardness is more than 2 times your alkalinity. You have some issues. We need to get an RO system, start all the way back from the beginning, and we're going to use a best min to then bring it into that green area and focus on taste. Now, with that RO, that soft water that we saw in this first one, that's when we start seeing the ability for pitting. It's going to start transferring those electrons and all these different things, and find areas to start causing holes within your boiler. It's going to start corrosion within your boiler. So it's really bad to stay right there.
So that would be anything in the blue right there, right?
Yeah, so how we get out of that blue and ride that train up on that slope is we're going to start remineralization. So we can use a best min to do that if you're in a plumbed environment for your espresso machine, or can do that. If not, then we can actually add some things. So there's lots of different companies. Third Wave Water is one. There's lots of ways to remineralize your water. Epsom salt being one, baking soda. Those are different things that you can actually increase this, right? So we're in this nice Goldilocks green area now that we're focusing on taste, really defining it. Now, the next part, outside of that 6 degrees hardness, is when you start getting to what we consider hard water. I would consider hard water. Too hard of water for our espresso machines. So this is when there's basically not enough of these. There's too much. Let's just say there's too much of everything for this to then actually evaporate in any sort of way or come out into your cup. It's going to be left over, and as your machine cools down, it's going to stay there. It's going to re-solidify at that point, which is really bad.
Meaning become scale.
Exactly. That buffering is not working to the best of its ability. It can't quite get there, So anything in this red area, specifically on that 1-to-1 slope, in that red area, I start recommending something like the Best Max Premium that will do that ion exchange, as well as that Best Max, the Aqualizer Pitcher.
The Best Save M.
The Best Save. We start getting into that.
sachets. Yep.
Yeah. So anything in that darker area. Now you see this graph starts to fade out. It starts fading away now, right? Out there is when I don't even touch it with a 10-foot pole. So out there is when I start recommending an RO system. Your water is way too hard. We need to bring that back as close down to 0 as possible. But remember, as you have an RO system, it also usually brings things back down into the same ratio. So if you still have a lot of issues with your water, you need to figure out what those special cases are. Because if you have a really high total hardness and a low alkalinity, it's going to come right back down in that same ratio. So really watch out for there and really remineralize at that point to the best of your ability for things to really taste good. As you can see on here, there's other units that you might see. So French hardness, you see Clark's, you see, what are those micromoles per liter?
Right.
So
and
all
I
of
don't,
these to
I don't
ppm.
see too much of those on, when I'm reading local municipality water reports or anything like that, but they can show up here and there. But there's some conversions right there for you.
So when we're in the red, it's too much, and that's probably going to produce scale. We need to bring it back down. We're using filters to do so. So that is the important feature right there. So,
So if you're too soft, you got to remineralize to protect your boiler. If it's too hard, you're going to have to get an RO system, then remineralize.
to protect from limescale.
And there's
So-
a few points in between where you're not going to need an RO system. All you're going to need is like an Aqualizer pitcher from BWT, a Best Max Premium filter kit if you're plumbing your water in, things like that.
Now there is a little bit of calcium and magnesium that is good to kind of coat as like a protective layer. I hate to say it, but they used to describe this layer like Teflon. But it's a kind of like a protective layer against everything from really building up. So within that layer, things are looking really pretty. And it often happens with things like copper or brass as well. It's really good for it though.
I have seen studies that a little bit of that layer is good, partly because it can protect the machine a little bit. We're not forming giant rocks of scale or anything like that. Plus a little mineral content. There are sensors inside of your boilers. If your water's totally empty, not only is it not good for the boiler, but the sensors are not going to read that anything is there anyway. So you need a little bit of mineral content so that those sensors can actually detect something and work properly.
Now watch out when you descale though after like collecting a whole bunch because you might actually clog your system. If you've watched any of our live streams based off of cleaning, we talk a lot about that. So if you were in that red and maybe you forgot your filters for a while or your ion exchange actually depleted, that can be an issue. You can start actually producing limescale after it's not doing this ion exchange anymore. So or filtering out. So we can start producing that scale, which is really bad.
Well, I'll tell you what. I think it'd be fun to do some tests.
The next part.
And I would also like to pull you another shot with our custom water here too.
Wonderful. I'll move my flocculation out of the way. And coagulation, don't forget.
Don't forget.
Don't forget. All right, so BWT test drops. So technically called a titration. Sorry, I'm trying to find the camera here. There we go.
You and Will are doing a dance.
Yeah, so these are our titration drops here. So I like to keep these in my purse or my MERS or whatever. I keep these everywhere. You want to keep them around room temperature though, because if you do see these drop, what you might find is that your tests might turn a different color, specifically yellow instead of red. So that
like if they're in too cold of an environment, that type of thing.
Exactly. So specifically within shipping. Now these test drops will work just the same. Still pay attention to your numbers and everything like that. Just keep in mind that the color ain't adding up. So what I'm going to go ahead and do is I'm going to look at this first one where it was like a potassium bicarbonate.
So this was empty water, just very high alkalinity, right?
Exactly.
Okay.
So I wouldn't say very high, but we'll see.
Okay, cool.
Oh, I actually have some sludge in here too, so this is not going to work very well.
Okay. I'll tell you, you got some more of that right back here.
Yeah, so I actually have it built back here.
Nice.
So we'll grab it from the source, direct from the source.
Get it right from the source.
All right.
Now, the way these work, you do have to count the number of drops that you're putting in each vial. And you'll know that each drop is going to be 1 degree of hardness. And you can follow that on that scale that we showed you, that graph. And let's say if you've got 5 degrees of bicarbonate hardness or alkalinity, you're going to follow that over with your finger right there. Okay, we're at 5. And then you're going to do the same thing on the other axis with your general hardness.
Now everyone's going to have to count along with me because I always lose count. It's like my special power to lose count. So I have carbonate hardness is going to come up first.
Okay, here we go.
Actually, no, lies. I'm just going to go over here.
Other way around.
So I'm going to go total hardness.
Nice.
So as soon as this thing hits green.
1, and then you have to
stir it in.
Stir after every single one so you can actually see what it's doing.
It's already about green.
Okay. So that's 1. This would be 2.
I mean, yeah, it's basically 0. So
cool.
What we're looking for there is
we'll
call
it 2.
It's empty water right there. Okay.
So
let's go ahead and go on to our carbonate hardness. What we're looking for here is a change specifically labeled inside this book. If you take out this little packet right here, we actually can see what color we're wanting to change into. Oh, I can't get in the camera. And you'll never be able to read that. Wow, look at that.
Well, I'll tell you what, if you grab one of these kits, one of these BWT titration water hardness test kits, then you can open up that booklet. It's going to give you way more information than just what color.
So we're going from blue to red. So right now we're still blue. We're at 1.
So we want to be red, and that's number 2. We're still not there. 3, close. No, nope. 4, 5. So we're at 5 degrees of hardness. There you go. All right. 5 degrees of hardness. So we pretty much had 5 degrees of general hard. No, that was alkalinity.
No, this is
right?
like 0. I mean, it was supposed to be 0. It did turn green.
Okay.
I just did another one for fun.
Okay, so pretty empty water, just about 0. And then we've got 5 degrees of bicarbonate hardness or alkalinity.
Alkalinity. Yep. So that is why things tasted, sour. It was just about there, I would say.
Just not enough mineral content to actually perceive taste.
It was buffering away a lot of the acidity, so it was really coming through. But is that safe in our boiler? Some may disagree. I disagree. Some may disagree. I don't know. Okay, so as we keep going here, okay, that's what we're looking for. Now we need to match that. So let's go ahead and do this BWT test again. This one's specifically done within tap water, and then it actually went through a new aqualizer pitcher.
Nice.
So
okay.
I'm going to go ahead and...
Yeah.
Just kidding. I'll just dump it right there. Whatever.
Let's check it out.
So normally you'd be not going back to back with all these different waters, so this might be tainted in results a little bit, but we'll find out.
Well, the sample size is big enough that we should get a pretty good idea of what's going on here.
All right, so we just use 10 milliliters. All right.
Now that's going to be now that's going to be 1 degree of hardness per drop.
Correct.
All right.
All right.
So we got an ECM. Oh, you got the Synchronica 2 coming soon. Nice.
Who's counting with me?
You're on your own for this one.
Okay, 1.
You got the BWT Aqualizer, and you're at 54 ppm. I'll tell you what. ppm, if you divide that by 17.85, that's going to be your conversion number there. If you divide that by 17.85, that's going to tell you what your degree of hardness is. So let's see, your alkalinity is very low, changing after 1 drop. Is that a side effect of using the pitcher? Is that fine? You may want to modify. Sometimes if you have low alkalinity and your general hardness is higher, more than double your alkalinity, then you might have a risk of gypsum.
All right, so I have a 2 and a 3. So I'm on the low side. So it actually took out quite a bit. So I would actually have to look at our tap water specifically to see, okay, what did we start with?
Sure.
So maybe this pitcher isn't like the best choice for that.
Okay.
Or it's a brand new pitcher, which just happened.
Sure.
But this is actually a different faucet than I've actually tested before.
Cool.
Most of our Rochester water around is actually pretty good. But this actually brought it down to, I mean, just the cusp of getting into our green area. So this water actually might be pretty nice for something like our coffees where we're trying to increase that acidity. It's definitely on that low side of things.
Sure.
It's not going to necessarily produce any pitting at that point. It's pretty unlikely. But it might be on the acidic side. So how we would actually go from there is starting with a different water base, maybe a different tap, because they're all going to be different. Lots of different things that we can do from there. I know specifically, I always get my water from the kitchen because that brings it all the way down into this like nice 4 and 4 area, 4 and 5, and I do my little happy dance every time.
That's your sweet spot.
Yeah, that's my little sweet spot. So specifically, this new little kitchenette that we have over here might have a little bit different water.
I'd be interested in comparing that with the one in the kitchen. We're going to get nerdy a little later too.
We got some ideas. Okay.
So I'll tell you what, how about that custom water? I'm interested in how that's going to taste.
So let's go ahead and test this before we taste.
Sure.
Right?
Sounds
I just want to see how crazy we are. You know? So we'll see. So crazy water. I don't know.
So what'd you do here to get this this custom water? What'd you use?
I used a heavy hand, John, a heavy hand.
So this is a pretty full water.
Yeah, so I've used different kinds of bicarbonates. I've used different kinds of calcium. I've used another pretty interesting thing that we do not want in our water, but we see it occasionally, sodium. We don't like sodium. You know why? It's the same reason why our trucks are corroding. Well, my truck corrodes on the bottom side, starts rusting. Sodium is a great conductor, you know?
Okay.
High conductivity. It's a little bit easier to kind of surround it and break it apart. When we were talking about molecules earlier, it's very soluble, and then it solidifies, or no, it's very soluble right away, and then it travels those electrons really fast.
Wow.
You get what I'm saying. Little electrons going back and forth.
High energy just from the salt.
Lots of energy, just like me. All right, so we have our 10 milliliters, and we're going to go ahead and test each one.
Let's see what this custom water came out to. I'm interested, especially because we're about to brew with it. 1, 2, 3, not red yet. 4, you're actually getting my help on counting this time.
Perfect, because I lost count already.
5. I got your back. 6, 7, and this is the alkalinity, right?
Yep.
That we're testing first. 8.
Do you see how it's just getting darker blue?
9.
Isn't that horrible?
Wow. This is heavy water.
Okay,
10.
so right around the 10 point is when I'm like, do I even want to waste drops anymore?
Sure. 11.
Might not want to waste any drops anymore.
12.
So what we're seeing here is that we have a very high buffering capacity. I'm going to stop there because I don't know if we'll find an end to this.
Sure, yeah.
Which is very possible. Some people are like, I use 32 drops. Don't get to the point where you're using 32 drops.
Once you get to that point, you already know what needs to happen anyway. So
Exactly. So that's deep sea blue right there.
Yeah.
So let's go ahead and go on to our total hardness here.
And you did make this extra wild and wacky on purpose, right?
Yeah, I want to see how it tastes.
Yeah, this is not a surprise right off the bat, but
nope. All right,
that's
so what
2.
we're going for is green.
3, 4. I wouldn't be surprised if we end up with a similar result here. 5, 6, and at 6 we're pretty much out of the point where we're at the point where we need a BWT Best Max Premium kit or an Aqualizer. That was 8. I am counting.
I was at 7 and 8, 9, 10.
Let's go with 9. Yeah, we'll
let's
go with what you have there.
I don't think we're ever going to reach an end.
Yeah,
okay,
so this is really hard water. Wow.
Really, really hard water. So let's go ahead and taste it. So
let's do it.
The idea that we've set now is that this has a lot of buffering capacity. There's a lot of salts though, so that helps flavor, right? It's like salting a steak. If it's really raw, it could be really good. But I mean, as an RO system, I like to describe that as eating a raw steak. And then there's just a right amount of like seasoning, and then also cooking it will actually bring it into the good area where we actually want to eat it, or in this case, drink our water.
Yeah.
And then there's going way beyond that, and I've done a huge dry rub, and I've then seasoned on top of that, and then between my seasonings, I seasoned it again. That's basically what happened here. So I have like an over-seasoned, parching mouth steak.
Yeah. Yeah. Just over the
top
top salty.
Just thinking about it. So that is what I'm thinking will happen to our water because of this crazy experiment.
All right.
But there's only one way to find out, and that is by John pulling a lovely shot on our E24 Gaja Classic machines over here. So we're dealing with brass boilers too, so I might even open this up later and see all the little deposits of whatever we got going on in there. And we'll also maybe take a little TDS as well. So
sounds fun to me.
We do have one TDS meter. I typically like to use this TDS meter, again, total dissolved solids for our coffee specifically. Now, a big thing that I like to touch on as well before we finish up this stream is that between all of these, we notice that it's perception of sweetness and taste is changing throughout But realistically, besides if our TDS is super, super high, our TDS throughout these extractions, we're not extracting the coffee any more or less. Because our water is so empty, we're not extracting more of that coffee. And because of our water being so heavy, we're not extracting more of that coffee. Now, we are either buffering acid compounds and taste compounds and aroma compounds, or we're not. We're buffering too much so it doesn't taste that good, or we're not buffering anything at all, so it's just like, whoa, an explosion of acids and whatever coffee. And that's the common misconception too, is that, oh, you can extract more coffee, more things, higher TDS on empty water. No, that's not how it works, actually.
Interesting.
No, it's just flavor, taste compounds and things like that are being perceived a little bit differently throughout. So, I'm kind of scared.
I am too. This is going to be a
all right, cheers.
Salty one. Let's go. Tell me what you get.
So it doesn't taste like anything besides sodium?
This is a pretty salty shot.
It's a pretty salty shot. It's kind of weird because it loses all of its sweetness and all I can get is just like straight savory. So if you have savory shots at home, I start recommending looking at your water. And in fact, no matter what, I do want to come out of this live stream saying, no matter what, look at your water, use a filter, pay attention to your water, because that's what's really going to define your taste and really dive into this huge thing. So a lot of your water might look like this. I hope not. But these tools behind us from BWT will protect us from that happening.
Charlotte says, the violent cringe of that was delicious. Yes. That was the look on my face for that one. And Zach, now I understand why you come at it with water first.
Water first.
Yeah.
Yep.
And after that, you can start playing with grind settings and things like that. But good stuff in, good stuff out. And if you don't have good stuff going in, guess what? Not too much good stuff coming out.
Exactly. And all the millions of shots that we've pulled through our decades of doing this and pulling shots and being in commercial, water is something that we've always paid attention to. Back in the day, not so much, but we've been learning so much about water now that we've never known before, including a lot of that research being done by BWT. There's Zurich doing a lot of research as well. Lots of people really paying attention to water now. So again, it's kind of like this golden age of coffee, water, and science that we're living in, and I'm really excited where it's going to be going. So a lot of home enthusiasts are paving ways, like our red machine over there, just doing buffering, which is kind of crazy. But I leave up everything to try it. If it doesn't work and it fails, well, that's kind of the era that we live in. We don't know everything right now.
Right. Yeah. Which is the most fun part of this. It's I've been in coffee 15 years, and the number of things that I've seen change since the beginning, it's wacky, out of control, and so much fun. And we're kind of on the cusp of all kinds of really great research and innovations. So this is a really interesting and really fun time to be in coffee.
Now, without me going into anions and cations and carbonic acids and how they're melting and your specific water and rain and melt and all of these things, I think we'll have to sign off for now and leave that for another time because we are out of time today. But thank you so much for joining us today on our little tad bit of water chemistry. My name's Zach.
I'm John.
And thanks for joining us.
Thanks, y'all. Cheers.